defined to be, like the result is going to be a scalar. So having the x.
Oh yeah, I do remember this. This is a typo I changed in class. I said knock off the x the next word. Yeah, I apologize.
Okay.
Can you?
Somebody was looking at this exam. I think it was this morning. There was another typo I caught.
Would it be easy for you to change that really fast, or?
On number 4, you had.
Here it is. I asked for the dimension of t, a transformation. That doesn't make any sense. It was, as I recall, a dimension of range before you actually find the range. So you guys, I'm sorry.
So.
I only remember this because it was last semester.
I think there was one on number 4 too.
Oh,
So just really fast. What do I have to change here?
number 3.
Okay.
You see this x and this x squared?
Yeah.
They don't belong there. This is supposed to be a scalar. And even with part 2, the x and the x squared do not belong. Oh, sorry. I meant this x does not belong.
That doesn't especially change it.
Yes. I see your point in terms of the manipulations that do or do not allow it to be an inner product. At the same time, inner product really is a scalar, not another element of the original vector space, unless the original vector space occurs.
So should we just cut off that whole x plus 1 squared piece also?
Oh, there it is. You're right. I didn't see it. Sorry. You got to cut off the x plus 1 quantity squared.
Okay.
That didn't work.
And what was the other one that we had to change?
Just when it asks for the dimension of t.
Well, instead of dimension of t in number, what was this, 2 or 3? In number 1, I wanted a dimension of the range of t.
It also says that on the first part of the practice.
Does it really?
Yeah, it just says
Oh, you know why? When I created the second part, I probably just cut and pasted and changed the transformation or something. That's why I duplicated the error. Sorry, Galen, I didn't get caught in the equation.
Okay, thank you for clarifying.
You guys know I write my exams, so I make these mistakes.
Question 1.
On this section, this exam.
Yes, part 2. For question 1, for the determining the kernel of t, I was basing it off the quiz that we took in class, or the take-home quiz that we just turned in.
Thank you for reminding me.
The part that
Oh no.
once we solve for the kernel, like we said that matrix equal to the 0 matrix, that we get a bunch of terms. I noticed in the quiz that you added looked like if you notice in the original matrix, there is no A3 term. Why does the A3 term pop back into, I guess,
Into the kernel.
into the kernel? Yes.
All right, that's a good question. Because I think with this example, that's a really good question, by the way.
Can you actually just do this question?
Yeah, this is it.
All right.
I'm just curious. Is there anybody in this room who's able to just give me the kernel off the top of your head? Chris?
It's 3 plus x, comma x cubed, comma x.
That was perfectly put. I agree. But let me show you the details. I think the kernel of this transformation is simply going to be a set of all input vectors, that is to say 5th degree polynomial or below in degree, such that they get transformed to this. All right, just think this isn't working. To this. Which ends up being nothing more than the 0 vector. Well, I should say the 0 vector and the second vector space, that's M2. I just mean the 2 by 2 0 vector. Now, for this to occur, I think it's got to be the case that number 1, a sub naught minus 3a1 is equal to 0. And I think it has to be the case that this particular entry has to be equal to 0. And I think it has to be the case that this entry is equal to 0. Do you mind if I don't state the last one? It just duplicates what the first one says. But if I solve the system, the second system equations for a2 and a4, oh, I just did. I think it tells me that a sub 2 and a sub 4 equals 0. And I think over here, this equation right here tells me that a sub 1 is equal to 3 times a sub naught. So if I want the kernel of this transformation, then what I'm really looking for is the collection of all these elements of P5 such that they get transformed into the zero vector of the second vector space. And I think you and I just found that this ends up being nothing more than, I'm getting too sloppy, hold on. I think it transforms into nothing more than, can I just make a name up for x a sub 1? Can I call it R? But if a was R, I guess did it backwards, didn't I? I didn't say anything wrong, but my arithmetic would be easier if I allowed x a sub naught to be R, which means a sub 1 is going to be 3. So I think this fifth degree Pauling function looks like this. I said an R plus 3R times x plus, I'm missing the a sub 2, darn it, a sub 2 is yeah, a sub 2 is equal to 0, it's gone. And I said a sub 3 was, well, what does a sub 3 have to be so that this thing is equal to 0 vector?
Anything.
Anything in Darmo, please. Call it a sub 3 x3, that works fine. I'll call it s x3. Do you mind if I list the next one as tx to the 4th?
Yes.
You do mind?
I
Yeah, I do too, because I think when I saw the system over here, I found a sub 4 to be 0. So I think that coefficient of x to the 4th is 0. Am I missing anything? You're right, I'm missing x to the 5th term. Maybe I'm being goofy with this t garbage. Maybe call it a sub 5 times x to the 5th. Such that this r and s and t business are simply real numbers that range over the entire reals. Or let's just cut to the chase. I think this is nothing more than the span of the second tenney. How many elements? 3. Namely,
1 plus x. 1 plus 3. No. X.
I like them. Oh, by the way, the kernel, the dimension of the kernel is going to be equal to 3, which means, the original t is definitely not 1 to 1.
Chris, will you forgive us if we don't use those variables r, s, and t, and we just go straight from the original coefficients to the span of something?
Absolutely, I'd be more than pleased, because that means you see it right away.
On, as far as notation, why is it A1 is equal to 3A not A naught is equal to 3A1?
That's a mistake, actually.
Because I can't do arithmetic?
Sorry. And then from there,
My apologies.
so where did, what?
Well, can I change it officially, though? I don't want to leave anything that's incorrect on the ink board. My apologies, you guys. So what did I mess up on over here? If a sub naught, or if a sub 1's 1, I guess it does change things. And one more time, my apologies.
And so what, I guess, what is R, S, and T? I know R is X naught, but what was S replacing?
Because I just wanted I wanted to press upon you that I got 3 variables. S was merely replacing a sub 3, T was merely replacing a sub 5. As a matter of fact, Michael, if you wrote, instead of 3R, if you wrote 3a sub naught plus a sub naught x plus a sub 3x cubed plus a sub 5x to the 5th, I'm happy with that. It just means now you got such that a sub naught, comma, a sub 3, comma, a sub 5 range over the variables.
So, the book would normally do like kind of an intermediate step here where we factor out the R, and we factor out the S, and we factor out the T, so we combine them by terms and do that.
Although in
And
this
it looks like
example-
you just kind of skipped past that
I did.
and just, yeah.
Although this example is really no factoring out of the S and T, it's just separating them out.
Yeah, it's separate, well, yeah. Well, the R you'd have to factor out, obviously, but,
That's true.
so you don't care if we just kind of skip over a lot of that stuff and go straight to the span?
That's fine.
That's fine,
I'm happy.
okay.
Chris, do you have a question?
No, you fixed it.
Oh, so my mistake, my apologies. Chris?
Is there any sort of situation where it would be useful to know the basis of the kernel? Because, I mean, it looks nice to write the kernel as a span of some vectors, but it doesn't really, other than being a set of units, I don't see the point of that.
I think, oh gosh, that's a good question. I think there's a big point. Because if this transformation were a matrix transformation, I think the kernel represents the null space. but it's a subspace, the original vector space, that actually passed through the origin. Because the null space is setting up a system where A times x bar is equal to 0 bar. And so I think that's the way you're going to get a subspace of some bigger vector space, is when you pass through that origin. So I do think that's important.
Can you go over the range portion of
Yes,
this?
I could. I'll do that.
So what was the main reason that A sub 3 and A sub 5 get placed into the first section?
Here's one. Because I think no matter what A sub 3's excuse me, I'm going to slow up again. I'll slow down. I think no matter what the numbers A3 and A5 are, even if they're non-zero, I think this matrix right here getting sent, this matrix, I think this LMP5 getting sent to 0 element makes no difference what they were, because they're nowhere in the output of this function. This transformation's output is only described in terms of things other than A sub 3 and A sub 5. So A sub 3 and A sub 5 range freely over the reals, and they still get transformed to 0 vector, or through this transformation, you don't even see them. They're completely irrelevant. Their values are irrelevant in terms of generating that piece to the second vector space.
Right, and then, so as far as the brace notation, so the part to the left of the vertical line, that's representing P, not T sub P, or,
Yes, I think to the left, I'm looking at some collection of elements in P5.
Just out of curiosity, I'm sorry, this is slightly off topic, but do we have a standard inner product for line number 2?
Yeah, I think so. I think your standard inner product will look like this. Doesn't it look just like the standard inner product
Yeah.
on P starts at slope 4? Well, except missing the constant terms.
So you can have more orthogonal matrices.
Oh, absolutely. Yeah, in terms of looking at an inner product, if they have to be orthogonal matrices, it just simply means your inner product values to 0. Which certainly could be the case. Anybody else since I stopped? Okay. All right. And you wanted to find the range?
Yes, please.
I'm just curious. Or is there anybody here who could just spout it all?
1, 0, 0, 0, 1.
0, 1, 0, 0.
0, 1, 0.
Let's see if we made a mistake. What was the dimension of the kernel? I erased it, I know, but what was its dimension?
Wasn't it 3?
3. What's the dimension of the range? If we're
3.
right. 3. But the sum of the two better be equal to the dimension of the first vector space, which is 6. Thank goodness. Brad, you see why I'm listening it so fast?
Well,
Because when I look
yeah.
at this 2 by 2, there's
see
too much
that-
of a tight restriction between these two entries.
Yeah.
They've got to be the same.
I see that.
But these two, I think, are completely dependent of each other.
Yeah.
As A sub 2 and A sub 4 range over the reals, I think both these entries range over the reals as well. And that's why I think, in a sense, they're independent of each other in the set,
Yeah.
which is a big limiting set.
How did you get the 6 though? That's what I'm
Oh,
still a little
sorry.
confused about.
Let's come back.
I see that.
I know I erased on the board, but remember we had the kernel listed?
Yes.
And using span notation, there are 3 elements in there.
Okay.
Or from the previous step, I had 3 free variables, R, S, and T.
Okay.
So for both those reasons, I think the dimension of this kernel was 3.
Okay.
I think as you glance at the range the way I wrote it, since the spanning set consists of 3 elements, then the dimension of the range is going to be 3 as well.
Yes.
But the sum of the dimension of the kernel and range has to be equal to the dimension of the first vector space,
Oh,
which is
yeah.
5.
Yeah.
And I think
Okay.
it's
3
dimension
3
is
plus 3
6.
rank and nullity. All
So
right.
the fact that 3 plus 3 equals 6 is verifying that indeed the general rank nullity theorem holds true
Yeah, I got it.
in this particular example.
Yeah.
Better?
Yeah. And what about the well, there we can't find a inverse because
Well, no, in generating the inverse, what happens?
well it's not 1-to-1, so
Good, all
we
heck
can't
breaks loose
find
because
it
I don't
there.
have an isomorphism. It's not a one-to-one onto transformation, so I can't create an inverse transformation.
Okay. Can you briefly just explain isomorphisms really fast?
Isomorphism is this easy. If you've got two vector spaces, V and W, if they happen to have, well, let me make a full sentence. If there exists a linear transformation T from V to W that is both one-to-one and onto, then we call this transformation T an isomorphism.
Okay.
But you guys, I'm saying this very coldly in terms of my definition. I mean, what's really going on when you have an isomorphism, however, is it really means basically every single one element of the first vector space V gets mapped to a single one element second vector space, and vice versa. There's a one-to-one correspondence. And that also means I can create an inverse transformation. It means I can undo whatever my transformation T does. And it also means this. If you put on some special mathematical glasses, where you do not see the details of what the elements of V and W look like, whether they're matrices, polynomials, ordered n-tuples, don't look at any of the aspects of their application, don't look at the symbols. Then with the special pair of mathematical glasses on, boiling V and W down to their pure mathematical essence, so you see no impurities of application or even symbols, they end up being the same set. They behave in the same fashion.
Okay.
That's what an isomorphism really is.
So when you state that, like in this case, V and W are isomorphic, do you have to state what that transformation is doing? Because like, what if it's
Oh,
isomorphic?
depends on the question. If I asked you, is a linear transformation an isomorphism, all you have to do is say, well, it's one-to-one and onto, so yeah, it is. But if I ask you to create an isomorphism out of thin air between two vector spaces, then I want you to build a transformation. So I think they're two separate issues.
So I was trying to think, like, if you say two are isomorphic, but like maybe there's some transformation that doesn't work, but some that does, then.
No, that's true. So to say that there's an isomorphism means you can go out there and find a transformation. That's a linear transformation that is one-to-one onto, although I confess, yeah, I'm sure you can find, I know you can find many transformations that are not one-to-one onto.
Is there an easy way to do that? Find an isomorphism.
Usually it's a very natural relationship. For example, what if V is equal to this? And what if W is this? Ah. Clearly, since those two vector spaces have the same dimension, you could create a thin air isomorphism. And I think there might even be a natural one.
Transformation from V to W. Okay, A1, A2, A3, A4. Equals, wait, you're closing.
Thank you.
A1 plus A2 plus, or I'm sorry, A0 plus.
Well, I gotta stick with these.
Oh,
I know I use something different in terms of subscripts up there, but. Yeah, I think this is a very natural isomorphism. You know, if you read any more advanced mathematics, we have a name for that. We sometimes refer to it as a canonical mapping. It just means natural.
can you have an isomorphism from vector space with a different dimension to the?
No. Well, only if you consider to mapping to a subspace a second vector space. But it wouldn't be an isomorphism for the first vector space to the second vector space. I had to restrict my attention just to the subspace. I'm mixing words. To answer your question directly, no. Because the two spaces have to have the same dimension. But I could cheat and say, oh, don't consider all the second vector space. Consider a subspace of it, which by the way is a vector space in its own right. Then I can create an isomorphism between those two.
So if there exists an isomorphism from a vector space to another vector space with a different dimension, that necessarily applies to
necessarily, because they can have completely different looks, like in this case right here. Completely different looks. And so the second vector space wouldn't be a subset of the first vector space because one's M2 and one's P.
Well, I said they have different dimensions.
Well, yeah, I know, but even if I consider it this one. There's no isomorphism between those two. But there is an isomorphism between V and a subspace of P4 that has dimension 4. But just because there's an isomorphism between the vector space V and the vector space, which is a subspace of P4, doesn't mean the subspace of P4 is a subset of the first vector space. Because the first vector space can be completely different, like in my example, where it's M2.
Would you mind doing the next problem, number 2 on part 2?
So number 2, part 2. Oh, you asked the most beautiful question.
Oh, I actually know the one.
Is that it?
You can do that one though.
That's got me.
You really want to.
What's the question?
Actually, yeah, that was all.
Yeah.
It's determine if each of the following transformations are linear.
You feel so alone. You know, when you're lonely, you feel
Yeah.
alone.
U bar times, are you asking for an instance?
Tell me what to do next. What color do you prefer?
3.
Which one?
3.
Which one?
Is there actually a correct answer to this question?
The color is none. I think I need to use eraser. Because what is this thing upstairs? What is that?
It's
Inner
inner product.
Wait. You said it's an inner product. That means, I don't know which one it is. Michael?
Well, since it's not listed, isn't it alright to assume that it's linear?
I can't even use that adjective standard because I don't even know what the vector spaces are. Oh, is that abstract? What you guys are missing is the fact that we're not using our properties of inner products. I can't split up over the second entry, can I?
Oh, no.
Just switch them.
Thank you. But I need to show you, the reader, that I'm doing that because it's an abstract inner product. So I guess what I really meant to say was this. I've got V bar plus W bar inner product with U bar since inner products commute. Now I've got the mathematical legal right to separate. To separate correctly, by the way. Sorry. To continue to separate correctly, I'll get there. But this is the same thing as oh, you guys, I'm getting lost. You tell me what to write next. Or tell me what to do.
The transformation to E.
You said trans.
T.
Well,
I would just prove that you're done to show that T is V bar.
Gotta flip and show that. I gotta use a commuted property. So, like Daniel was pointing out. Did you guys see my point? As I recall, things didn't go over very well with that question last semester. What's next?
Now it's T is U B.
Yeah, proclaim your happiness. Doesn't this just give me T evaluated a V bar plus T evaluated a W bar? I've shown that first linearity property.
Awesome.
Well, now you get to show the second one.
No, that's true. But you get the idea. Oh, yeah. Oh, yeah.
Wait a second,
Yes, I'll wait.
hold the phone. So it's not one of our axioms that that it doesn't distribute from the other side?
In a sense, it does. It's just that I have to show that using my axioms for an inner product.
Can we just add a new axiom?
Oh, what a good question. Historically speaking, this has happened quite a bit. So if I'm going to create another axiom, I want it to be completely independent of the other ones. And I think it wouldn't be an axiom in that case. That would be a theorem that you could
Then
prove.
can we just accept that theorem's true? Can we say we proved it in class?
All right,
And that's
maybe I
trivial?
did a poor choice in wording this question. I meant to say, verify it using the properties that we know of these things.
Okay, so we have to
You should assume that.
commit all these axioms to memory, rather
Well, when you
than
say all of them, it's just 4.
you giving us the axioms on this exam.
But you know, in your heart, you wouldn't feel as comfortable after the exam if I did that.
Oh, I feel great.
I agree.
Oh.
Touche. Michael.
So, but is this question, do we have to use the 4 axioms in this question, or was it?
Can you back up? I just didn't hear that. I'm sorry.
For the question that you just did, are we using the, I guess, test to see this linear transformation, or are we using the 4 axioms to?
How about saying it this way, Mike, this combination? The question was, is this transformation linear? So I have to show that first linearity property. It's just in showing that that piece is equal to that piece. Notice along the way I used the basic axioms of an inner product to get there. My vehicle was using the axioms of an inner product. But the punchline was to show the linearity properties hold for the linear transformation, and I did not answer the full question. I only showed that it's true that the first linearity property holds. Did you catch all those words? Can I say it again? To show that the first linearity property holds, to show that this T is a linear transformation, along the way I had to use those axioms of an inner product.
And then, as far as starting this problem, would we have to define what W was, since it's just
Oh, you know, I see your point. That's getting to splitting hairs. I can only assume that you understand I'm grabbing 3 elements from the first vector space.
So do you care in this one if we define our variables? So,
No, I think it's understood.
okay.
I'm happy.
Also, can you explain quickly what this bar means?
What barn?
So for axiom number 2 there,
Complex
the
conjugate.
bar, complex conjugate.
Yes. When it comes to the standard inner product on C,
Oh, so this is just for a complex, we would just use the
Complex
complex
space.
conjugate. Okay, I get it.
and the reason being we want the magnitude of a vector
Yeah,
to be a scale
we want it to be
that matches what
real,
we
yeah.
expect.
Okay.
You can define that as the general inner product. Well, I mean, it works in the real number system too.
Well, yes, because when you have a real number that's non-complex, its complex conjugate is itself, which brings us exactly back to where we were with the original axioms of inner product. Yes, I agree. That's why it's so nice how I can say, when you're dealing with complex numbers, you're also dealing with the reals in there. And everything you do with complex numbers still applies to the reals as a subset. You guys ask such good questions.
So, well, Daniel had a good idea the other day, that, when we're studying for the final, that if each of us went through like a chapter and we kind of categorized and wrote down all the theorems,
That's pretty cool.
and
Yeah.
then we'd each have like kind of like a good study sheet, and we
Yeah,
could just
that's
look at
very
all that, yeah.
As long as where you're going next isn't, what can we use on the test?
Well, of course, but
But you know what my answer would be.
absolutely.
Michael?
Okay, so to basically finish this, to actually answer if it's linear or not,
Oh, yes.
we would then do the next one where it's a transformation of constant times the
Yes.
variable, or vector in the first vector space. Okay.
I agree. Well, if that is okay, I will clear it out. So what did you guys think is gonna happen if I do this? Here's the x-axis. Here's the